In this video, we're going to talk about one important part of the chemicals world, polymers and advanced materials. You can think of this block as the higher spec side of plastics and materials. Instead of simple, bulk plastics used in everyday items, this area focuses on materials that solve demanding engineering problems. These are used where you need high temperatures, high strength, very tight safety rules, or very long life. In other words, places where failure is not acceptable. Most of the activity in this block falls into the following 5 main areas. 1. Engineered resins and specialty plastics. 2. Composites and electronic materials. 3. Circular platforms and application services. 4. Circular platforms and application services. And 5. Application development and OEM specification services.
Polymers and advanced materials sit in the middle of the chemicals value chain, between basic chemistry and finished engineered systems. They buy monomers, base polymers, additives, and fibers, and turn them into high-performance materials. These outputs flow into demanding end markets like autos, aerospace, electronics, healthcare, packaging, construction, and new energy. This is a strictly B2B space. The customers are OEMs and Tier 1 or Tier 2 suppliers who design cars, aircraft, and devices. Once they qualify a material, they expect reliability for years, which makes this segment technically critical and highly sticky.
First, there are engineered resins and specialty plastics. These are pellets or compounds that go into higher performance parts, such as under-the-hood auto components, medical devices, electronic housings, connectors, and structural parts. They include materials like advanced polyamides, PEEK, PPS, and high-end polycarbonates. They are chosen because they can handle heat, mechanical stress, chemicals, or regulatory requirements better than commodity plastics. The global engineering plastics market here is already well over $100 billion and has been growing faster than global GDP, helped by trends like lightweighting in cars, electronics, and construction. Second, you have composites and structural advanced materials. Here, the output is semi-finished products like carbon fiber or glass fiber composites, fabrics, laminates, or molded components. Customers use them when they need high strength-to-weight ratio and long service life. You will find them in wind turbine blades, aircraft structures, high-end sporting goods, pressure vessels, some auto parts, and infrastructure. This is also a very large market, again over $100 billion, growing in the mid-single to high single digits each year, driven by aerospace, autos, and especially wind energy. Third is electronic chemistries and materials. These are used to make and package electronics, photoresist, dielectric materials, specialty polymers for chip packaging, encapsulants, and circuit board substrates. They must be extremely pure and reliable because they sit inside semiconductor fabs and electronic devices. This area is expected to grow faster than global GDP, supported by rising semiconductor volumes, AI hardware, 5G, and automotive electronics. Circular and recycling platforms aim to close the loop on plastics through advanced mechanical and chemical recycling. They produce recycled resins or monomers for high-spec use and may license their technology. Growth depends on recycled content and responsibility policies. Application development and OEM specification services help customers in packaging, automotive, electronics, and medical industries design and test parts, locking materials into long-term specifications. Customers are mainly businesses, auto, aerospace, electronics, and medical OEMs, suppliers, packaging converters, and renewable energy firms. In the value chain, this block sits between basic chemicals and finished systems, buying monomers and additives, creating engineered resins and composites, and supplying industries like autos, energy,
healthcare, and construction. From an investment lens, polymers and advanced materials usually earn stronger margins than commodity plastics because they solve mission-critical engineering problems. When a material is qualified into an OEM design, switching is costly and difficult, which protects pricing and returns. But returns can weaken when there's overcapacity, when products get commoditized, or when feedstock spikes cannot be passed through. Demand is driven by sectors that require performance and reliability: autos, aerospace, electronics, wind and solar, medical, and high-end construction. Finally, regulation, sustainability, circularity, and the cost of capital are increasingly important drivers. Companies that navigate these well tend to sustain superior long-term returns. Polymers and advanced materials are moderately cyclical, but they hold up better than commodity chemicals because so much of the demand is tied to performance and long-term OEM specifications. When industrial production slows, however, OEMs build fewer cars, aircraft, and electronics, and that translates into lower volumes and utilization for material producers. Macro conditions also matter through the cost of capital. High interest rates can delay major projects like wind farms, aerospace programs, or new plants, reducing demand and increasing project risk. Input cost spikes in energy or feedstocks can also compress margins, especially for less differentiated producers. But there is an important stabilizer. Once an OEM has qualified a material, they almost never switch, even in downturns, because the risk of failure is too great. That stickiness helps protect both demand and profitability through cycles. Over the past 3 to 5 years, this block has been shaped by several structural changes. Sustainability and circularity have moved to the center, with stronger regulations and new recycling technologies beginning to enter commercial use. Composites have benefited from major demand drivers: wind energy, electric vehicles, and recovering aerospace, all of which need lightweight, durable structures. Electronic materials have gained importance as semiconductor content rises in autos and as AI data centers and advanced packaging require ever more precise chemistries. Finally, digital design and simulation tools have accelerated development cycles and made application co-development with OEMs far more central. Together, these shifts are increasing both demand and the strategic value of advanced materials suppliers. Looking forward, the outlook divides naturally into near, medium, and long-term dynamics. In the near term, specification stickiness and slow-moving capacity provide stability, though demand varies by segment, with EVs, wind, and recycled content materials still gaining momentum. Over the medium term, structural forces take over. Engineering plastics, composites, and electronic materials are expected to grow faster than global GDP as electrification, electronics intensity, and renewables expand. In the long term, high-performance materials remain central to efficiency and durability, regardless of how chemistries evolve. We can frame this in 3 scenarios: an upside, where decarbonization, EVs, renewables, semis, and circular platforms accelerate growth; a base, where electrification and digitization progress steadily; and a downside, where weaker growth, policy delays, or overcapacity pressure margins in weaker niches, even though demand for truly advanced materials remains.